Hi and welcome everyone. In this video, I want to go over problem number 4F from section 8.2. So basically, you're given a 3 by 3 matrix and you want to find the eigenvalues and the eigenvectors, and of course, the dimension of the eigenspaces. So to find the eigenvalues first, we need this matrix lambda I minus A, or you can do A minus lambda I. Doesn't make a difference. Please watch my previous recordings on finding the eigenvalues. And I did lambda I minus A. So if you do that, you get lambda minus 19 over 4. And since it's minus A, you change the signs of all the other entries. And this becomes lambda plus 9 over 4 and lambda plus 3 over 4 here. So on the diagonals. Then you can do it to find the determinant of that matrix. You can do a first row expansion. So it's going to be that entry lambda minus 19 over 4 times the determinant of that 2 by 2 matrix. And I did that here. So it's going to be lambda plus 9 over 4 times lambda plus 3 over 4 minus 2 times 2, which is 4. And it's negative 2 right here times the determinant of that matrix, which I wrote here, and I'm sure you know how to find that determinant by now. And it's 2 times the determinant of that matrix. And that's what we have here. Now we can simplify this, so you can expand that expression here in the first bracket or in all of them. And then if you simplify, then you're left with lambda minus 19 over 4 times. So you simplify that is lambda squared plus 3 lambda minus 37 over 16. And this, if you distribute the negative 2 and 2 to this brackets, you get that expression. Then you can, of course, expand that and then combine like terms. And that's what I did here. So it's you get lambda cubed minus 7 over 4 lambda squared. And I took all the coefficients of lambda and then found the LCD. This is just arithmetic. And then I took all the constant coefficients or constant terms, and I found the LCD, which is 64. And if you do that, you get that. If you combine, you get lambda cubed minus 7 over 4 lambda squared plus 16, 7 over 16 lambda plus 15 over 64. So this is the characteristic polynomial that you want to take that and put it equal to 0. One thing is good to do is multiply by LCD. So you can get rid of the denominators. And if you do that, you get 64 lambda cubed. 64 divided by 4 is 16 times 0 is negative 112 lambda squared. 64 divided by 16 is 4 times 7 is 28 lambda and plus 15 because the 64 cancel each other. Now that's a third degree equation and you can't solve this by factoring. So you have to use the rational zero theorem. And again, watch my last videos. The constant coefficient is 15 and the leading coefficient is 64. So you put 15 and all the possible factors of 15, you list them and you put the leading coefficient, which is 64, and the possible factors of the leading coefficient. And the possible zeros of this polynomial is going to be the ratio of all the factors of leading coefficient and the constant coefficient. So you can start with 1, so it's going to be plus or minus 1 divided by plus or minus 1 is plus or minus 1, plus or minus, well, let's just do it with 1. Plus or minus 1 divided by 2 is plus or minus 1/2. Plus or minus 1 divided by 4 is plus or minus 1 over 4. Plus or minus 1 divided by plus or minus 8 is plus or minus 1 over 8, and so on. Then you can do the same thing with plus or minus 3 and divide by all this number. And you get that second line. And you can take plus or minus 5 divided by all these numbers. And that's what we get. And plus or minus 15 divided by all those, you get this line. And this is pretty long. And once you list them, then you have to start the synthetic division. Now here, if you do the synthetic division, plus or minus 1, plus or minus 1 have one work. The first one that's going to work is plus or minus -1/4. And I put that here. Now, if you want to do the synthetic division, you can just go and take the coefficients of that first polynomial. This will do it too, but then it's just easier because it's plus or minus for each fraction, and we have all fractions here. So you can bring the 1 down, -1/4 times 1 is -1/4, so you get -8/4, which is just -2, and -1/4 times 8/4 is 8/16, and you get 15/16. And finally, -1/4 times 15/16, you get -15/64, and you get 0. So we know that -1/4 is a 0. You write the factor form, and these are the coefficients of this polynomial that you want to solve again. Now, this is a quadratic equation. Don't do synthetic division anymore, because now we have ways to solve it. You can either factor it or use the quadratic formula. You can multiply both sides by 16 here also to get rid of the fractions, and that's what you get. And this is factorable, so you get 4 lambda minus 5 times 4 lambda minus 3. So the second eigenvalue is 5/4, and the third one is 3/4. Now we have to find the corresponding eigenvectors. I did it for 1 for -1/4. So you just substitute this in the original matrix and you get that. Now here you have to find write the homogeneous system and solve it, or just find the null space of this matrix. So find the RREF of this matrix is going to give you that. Then you can rewrite the equation. Here we have one non-pivot column, and we know x3 here is going to be a free variable. So we can say x3 equals to t. Rewrite the system, x1 minus x3 equals to 0, and x2 minus 3/2 x3 equals to 0. x1 is also t, and x2 is 3/2 times t. You can write x1, x2, x3, then write t, 3/2t, and t again. You can take the t out, so you get that eigenvector. If you want only integers, then you can factor out t/2, you get t/2 and 2, 3, 2. So for lambda 1, which is -1/4, the eigenvectors are the span, the eigenspace is the span of this vector or that one. It's the same thing, these are just integers, and the dimension is 1. And if you can do, please do the other ones yourself. If you do for lambda to 3/4, you should get 1, 1, 1, and the dimension is 1. And for 5/4, you're going to get 4/3, 4/3, and 1, or 4, 4, 3, and the dimension of this one is 1 also. Please try to redo this on your own after watching it. And I think that's it for this recording or for this video. Thank you for watching, and I'll see you in my next video. Have a good one, everyone.